Oh, the first one.
First problem? Yeah, I mean, did y'all do it? This is straightforward. I give you the solutions and everything. Which one is it? Give me specific.
I think it was 6e to the j omega, e to the negative j.
No, I think it was this. Well, it might be from -3 and it went up to 3, and this is h of omega right here. And then, is that it?
It wasn't a graph on it.
No, I just defined as it is this. It says value for omega greater than 3, less than -3. But isn't the value of 1 there? Or is it e to the minus j3 omega?
Yeah,
It's 6e to the minus j2.
All right, so all around here, this is 6e. Let me write this up and then I'll graph it. H of omega is equal to 6e to the minus j3 omega times the quantity, go ahead,
it's just that.
forever?
Yeah.
No.
Yeah.
It says h of w is equal to 6e to the negative j2w. W is less than -3.
Yeah, that's it, minus 2w, right? And this is for omega, actually less than -3, right?
Yes.
And greater than, omega greater than 3, pardon. Right? That's omega W. Y'all see that? Well, this is from -3 to +3, so all through here, this is going to be 6e to the minus j2 omega. Here to here. I'm going to tell you this right now. This is the kind of problem I give a lot. I give you a graph or I'll give you a statement. I like giving graphs, and then you have to translate that into a mathematical statement. So you probably get this, and this would be 0 here. And that's h of omega versus omega. And what I want is the h of t, don't I, class? Now, you take a look at this. You first think, what does it look like? It looks like something that is what? Just a constant value with a bite taken out of it, doesn't it? So how could you get that? If I was just to do this first, I'll get back to this in a second. Ask yourself this. If you just wanted to have this, and this was my h of omega here, I'll call it h2 of omega. How would you define that? This is versus omega here? Well, what would you say? Wouldn't this be h of omega is just 6 times the quantity, 1 minus a pulse function of width 6 of omega? You agree that that would do it? Make sure you see this, right? A pulse has a height of 1, right? And the width is defined as 6. It's centered at this, where this quantity is 0 or omega equals 0. Now, do you all agree that that defines it, correct? With me? All right, now let me go ahead and just expand this. That's equal to 6 here. Then it's minus 6 times the pulse function with 6 of omega. And I want to go back to h of t on this one, just this one alone. But you all see what I'm up to. Now, from before, and you know these transform pairings, you have to kind of know the basics. We know a constant, if you have any constant 1, if this is x of t here, then the transform pairings x of omega, this is again small omega, is going to be what? 2 pi times delta of omega. We proved that with duality. Y'all recall it? Next thing we actually see is what? And I'll do it this way. I know that the pulse, right, with tau of t goes to here, it's going to go to simply tau times the sinc function of omega tau over 2, correct? And then using duality, I keep on stressing the importance of duality. You're going to see how powerful it is with dt of t's. Then if we take this function here, we take tau here, then we have the sinc, right? But not of omega, but of t tau over 2, right? And here, what do? I'm going to keep on harping on that. There's a 2 pi, right? Where for duality. Do y'all remember that class? A 2 pi here. And it's going to be 2 pi. Then it's going to be times this function, but now with t replaced by minus omega. Now in this specific case, can I leave this plus omega class? I'll keep on harping on this. Why can I do that?
Because it's even function.
Even function, correct? So this is omega here. Right? Now I'm going to do something to make things more appropriate. I'm going to divide both sides by 2 pi, so I get a scale factor of 1 over here. And now I can see this pulse function itself goes as that, right? Y'all agree? All right. That means if I wanted to take this back to the time domain, what would I do? The 6 would become what? Class, if I'm going now to the time domain, that's frequency, right? What happens? The 6 goes into the time domain, think of it, the DC term, it's right there, first one. 1 goes to 2 pi delta of omega, right? Well, actually, sorry, now I need to do, I didn't put the 1 down, sorry. What does delta of t go to? My bad. It goes to a constant 1, right? And therefore 6 would go to 6 delta t. I'm sorry about that. So this here would be just 6 times delta t. You all agree with me, class? Agree? What about the next function? Minus 6 times, well, what's the width of this function? 6, right? So if 6 was here, 6 would be here, right? 6 divided by 2 would be 3. That would be 3 over pi, correct? So I know we would go to 6, right? Because it was scale factor of 6, then it would be 3 over pi times the sinc function of what? 3t, correct, class? Please take a look at that. Do you all agree with me there? Everybody see that? Now that's for that function. Now, right? What do I have? I have this goes to that. What happens if I have this times a phase? If I have e to the minus j omega times some alpha, or plus omega times some alpha. What goes the other way? What does that always do? In the time domain, what is it? There's a phase in the frequency, a phase change in front of that, and frequency is always what in the time domain? Class? Time delay, isn't it? Do y'all remember this? Let me just put that here. If we have what? X of t minus, and I'll use alpha, isn't that just e to the minus j alpha omega times x of omega, class? Please follow me. Do y'all agree with that? What page are the properties on? If you don't see this right, this should be very readily apparent from the last, from the stuff we did before the test. For your, these are just Fourier transform tables.
I don't have like,
Or properties, what?
I think it's like 2.7 or something.
That's good memory.
228.
What is it?
228.
228? You all see what I'm doing here? So, what happens? Now, if I have this, right? I'm sorry. If I have this times a phase, I'm just going to go ahead and multiply. If I have this times e to the minus j omega times, what is it, 2 or 2? What does that do to this? It takes what? It does this, and say it again.
Just change all the t's to t minus 2.
Now, everywhere there's a t here, it's t minus 2. Do y'all see that? So now it becomes 6 times delta of t minus 2. And then it's minus 6 times quantity, I'm going to leave it this way, 3 over pi times the sinc, right, 3 times t minus 2. If you don't see this, if it isn't real apparent to you, please make sure you go through this and you can see these relationships. What I'm really trying to stress is, if you see something like this, the first thing you're keyed on, it sure looks like a constant value with a byte taken out of it. Right off the bat, you see that. So just go for it right away. That's this 6 times 1 minus p to this p6 of omega. That's just a pulse function of width 6. Right out the bat. Then get the transform pairing of that. Then think about what happens if I put an e to the minus j omega times 2 there. That's a time shift. That's all it is. Follow me, guys? This should, and the solution should make this painfully clear. Don't they? Did you guys do this or not? All right. Now, is there any other questions about them? It's a very, very logical. Yes?
Just one question. How do you get 1 minus p to the 6 of omega?
How do I get this? Well, 1 would just be this, right? If I subtract p to the 6, what does p to the 6 look like? Doesn't it look like this? So if I take 1 here and I subtract that, don't I get this? I mean, do you follow me? You know what a pulse function looks like, right? The pulse function itself, p tau of anything, of omega in this case, looks like this. This would be tau over 2 minus tau over 2, height of 1, that's omega. That's a pulse function. So if I subtract this from a constant, just invert it and add it. So then you get a null between minus tau over 2 and plus 2 if you got 1 there. You all see that, class? Honestly, how many see this? This should be very clear by this point. Very clear what I'm doing. I'm trying to get you to think. I call it the building block approach. The minute I see that, I see a constant with a pulse subtracted. That should be that fast, right? Now that I have that, just get the transform of that. Forget that phase business. Now once you have that, think what happens when you multiply by phase. It's always a time shift, right? Got one other question before we leave this one. Because I'm sensing there's some uncertainty. This is important. What if I asked you to do this one? This was one I did give you before. I don't know if you remember. Suppose this is my h of omega. Height here 1. This is going to be a b. This is a minus b. And I want h of t. How would you put a phasing? In
1 minus the
triangle function, right? Isn't that right, class? How many see this? 1 minus the triangle function. That would do it, correct? You know the inverse transform of 1. That's a delta t, correct? The inverse transform of a triangle function is tau over 2 sinc squared of omega tau over 4, right? There's a slight subtlety there, right? So that one would be a no-brainer. Do you all agree? I mean, it would be obvious, in my opinion, how to do it. What happens if I do this? And this is, say, B, and this is 2B. And this height is 1. And this is h of omega. Now, how do I get that? Tell me what it looks like. Doesn't it look like a triangle for starters? But it's not a triangle centered at 0. It's got a shift to it, right? So now your first job is to mathematically describe that. The mathematical description of it would be a triangle function, right? What's the width of the triangle function?
2b.
2b, right? Now, if this is omega, it could be t, but if it's omega, it would be omega. This has always got to be what? 0 where it's centered. Where is it centered?
B.
At b, minus b, correct? Now we go through the old method. Do you know what a triangle function is back in h of t? Yes. But now what do I have? I have something that has got a shift, like a time shift. What does that mean back in the time domain? It's multiplied by e to the j omega t, correct? Or omega in this case would be b, wouldn't it, class? How many see this right here? All right, so always think that way. Always think about it that way. That's one I give a lot, by the way, on tests. I do that all the time. Same with you. All right, any other questions? All right, see now, today we're going to do DTFT, and then we're going to hopefully have time to get into the DFT. That's something you can really process on real computers. We're getting to the point of applications. We're going to start talking about not just abstract transform pairings and stuff that are more useful for design, not true analysis, but now we're going to find out things that we can use for real analysis. We're going to do the DTFT. We're going to get the basic transform pairs. You know, that's what I really do. When I teach Laplace, Fourier transform, Z, DTFT, the thing you always look at is what are the transform pairs you need? And then the properties, because the properties allow you to get everything. So the transform pairs with DTFT, first you define DTFT, and that is x of capital omega is equal to the summation of n equals minus infinity to infinity, x of n times e to the minus j n omega, put omega first, j n omega. Now that is the actual DTFT. I'm going to put the inverse up too. The inverse you're going to like because it's identical to the Fourier transform. X of n is equal to the integral from minus pi to pi of x of capital omega times e to the j n omega d omega. And I'm going to tell you that looks, 1 over 2 pi, my bad. That looks almost identical to the continuous time Fourier transform, where x of t, the inverse transform, is 1 over 2 pi, the integral from minus infinity to infinity times x of small omega times e to the j, and this would be omega t d omega. That's the inverse for continuous time Fourier transform. Y'all remember that class? We didn't ever do that really. What did we always do? We used duality, didn't we? We made we threw in with duality to get all those inverse things. We never really evaluated that. It's doable. But there's going to be a very interesting connection between these two. This is, again, the continuous time Fourier transform, and this is the discrete time Fourier transform's inverse on both. All right? You'll see how powerful what I'm going to show you is and how it makes your life so simple. So getting back to this, what we need is some basic transform pairs. Now, I'm going to tell you a few things. First, I'm going to go through the basic ones that we already did. For this DTFT, I'm going to say this is my x of n here, and this is my x of omega. If you have a book, I'm not sure what page these are on, but this is going to be the DTFT transform pairs. I know. Where is it? 395? This is page 395. Now, the first one I always go for is delta of n. We did this last time. Just look at me one time. By the way, delta of n has a value of 1 if it's discrete time, not infinity. You all remember that class? Not infinity if it's discrete time, if it's a function of n, not a function of t, correct? Now, if you look at this, just plug it in here. The only place this is not 0 is when n equals 0, right? When n equals 0, I have 1 times e to the 0 or 1, and as you expected, a delta function in the temporal domain, or discrete time domain, is the same thing as really a delta function in continuous time. It renders 1 in the frequency domain. Next one has to be, and this is a property that allows us, but I'm going to put it in here. We did this last time, of n minus some constant. Doesn't matter what you call it. You can call it n minus, say, k. Where k is a constant. That would go to, think about it. Now this turns on at what? When n equal k, correct, class? Agreed? That's where it's 1. All other values are 0. So if n is equal to k, right? When this is going to be equal to, this would be n, would be equal to k, and this would be e to the minus j k omega. Or now it would be simply e to the minus j k omega. You all realize what I'm doing here? Throw that delta function in the definition of the sum, and it must be that, correct? Now, the next one, and I did this last time, and this is in the book, is if I have a to the n u of n. You all remember this one? And I said, this one, I showed you the trick. Do you all remember the trick I showed you about the summations? Everybody? I'm going to put it up here because this is so powerful. Write this down. Make sure you commit this to memory. I showed you how to do it, I think, the development of the proof. But I'm just going to define, if you have a sum of anything where n goes from Q1 to Q2, of a to the n, could be b to the n, doesn't matter, where I'm summing this, it's a geometric series. This will be equal to a to the lower one, q1, minus a to the upper one, plus 1, q2 plus 1, over 1 minus a. How many remember that? All right, remember the trick on how to do it? It's a clever little trick. But y'all all remember that? Just trust me, you're going to need to know that. Now, if you look here, we'll do this one just because it's important to see this. I hate to go over the same ground twice, but it's important to see this. Now I'm going to go ahead and mathematically evaluate that. So if we use the definition of the DTFT here, and I'll put it over here, and I'm going to say if I want the actual DTFT of a to the n u of n, now I put a sum here. Technically it's n equals minus infinity to infinity of a to the n u of n, right, times e to the minus j n omega. That's sticking it right in to the actual definition, correct? If you know this one, you don't have to write with it, just follow. Y'all agree? Now, here's where we modify this. What does that u of n do as far as the summation? It makes it start at 0, doesn't it? Because all other values are 0 for negative values of n. So just start it at 0 and get rid of u of n. What else happens? You see how I can group a times e to the minus j omega as a single term? I'll do it over here so you can see it. I can say that will be equal to the sum n equals 0 to infinity. Now it would be a e to the minus j omega here to the nth power, right? Right? Doesn't this look like that constant right there? Isn't effectively this equal to a constant? Right? A can be anything. It can have magnitude and phase. Do you all agree with that? So when you do this sum, you're really going to put this term right there, and Q1 is 0, and this term, right, it would be this value right there, and Q2 is infinity, right? So what this is going to be is really going to be, well, if I have anything to the 0, it's 1. 1 minus a e to the minus j omega here to the infinity. Infinity plus 1 is still infinity. Over 1 minus a e to the minus j omega. I'm going to make a comment here. If the magnitude of a is less than 1, this term goes away. All right, because anything less than 1 for an infinite power is 0. Do you all see that, class? So really, in the book, what they're going to have for this one, take a look at your book. They're going to have this equal to simply either 1 over 1 minus a times e to the minus j omega, or they'll have it as e to the j omega over e to the j omega minus a. One of those two things. And there should be a qualifier in that says the magnitude of a has got to be less than 1. Do you see that in your book? Look and see if you see that transform pair. You see it? You see how they have a has to be less than 1? Y'all see it? That's on page 298? Okay? And I'm going to tell you one other thing. If a wasn't less than 1, if it was 2, then this thing is geometrically growing to infinity, right? And one of the stipulations of both Fourier transforms and DTFT is the integral of just, or the sum of just the function has to be finite. It can't be infinite. Now, the one exception is the u of n. That's the one thing where it's constant. There is an exception to that. But in general, if the thing is exponentially getting larger and larger as time, or as n gets bigger and bigger, you do not have a DTFT of that. You're going to see something called a Z transform that is like a Laplace transform that will allow us to deal with that, but not this. So that's the transform of this, okay? That's 3 of them. There's a couple, let's see, a pulse function's the next one I'm going to do. And this will take care of all the functions you need to know. First the impulse, skewed impulse, then this, right? And then the pulse function. Now, if I have a pulse function, the way I like writing pulse, and he does it in his book, he has a little more, he has an expression that's kind of clumsy. I use the pulse instead of the rect function. I use p. and the subscript is the width. And I always like to say 2b here. I don't put a tau there, it's 2b, and then it's a function of n. Now what that function looks like, and I'm going to do it over here, so you see this, is this. If I have a pulse function of width 2b of n, it will be like this. And then all the other values are 0. Now, one thing you'll note about this, it's an odd number. Y'all see that? I have people say, well, the width is 2b. It's 2b plus 1, isn't it? I mean, really, that's 1, 2b, 3, 4b, right? That's 2b, but there's 1 at 0. Follow me? So just remember, that is an odd number. Got it, class? Make sure you don't forget that. It's easy to miss. What, Josh? You're looking at me like you don't believe it.
It's just weird.
Everything's weird today. It's all right, you'll figure it out later, but that's what you have to understand, all right? Now, something about this, when we get the actual the DTFT of this, I'm going to go ahead and put that in there, but can you all see that really when I'm going to do the DTFT of this, using this definition, the only thing I'm going to do is put 1 in here and start my sum at minus b, and in my sum at b. You all see that, class? How many see that? All right, because really, the pulse has a value of 1, right? And really, the only sums, the only non-zero values are from minus b to plus b. So when I do that, I'll do it here, I can say, this one's a little weird, so pay attention to this one. This is going to be for the pulse function, will be equal to, by definition, the summation of n equals minus b to plus b of e to the minus j omega n. Now, I, on purpose, put e to the minus j omega by itself and then put n in. Y'all see that, class? Got me on this one? Now, remember I put what this sum went to. So I'll put it here. Now I can say x of omega is equal to, it's going to be this. This is like my a, isn't it? Right there. A to the lower limit, which is minus b, correct? So now I have e to the minus, a minus or plus j b omega minus, and then it's going to be e to the minus j omega, and it's going to be the upper limit plus 1, or it's going to be b plus 1 here. All over 1 minus e to the minus j omega. Can you all see that, class? Take a moment and look at the definition of that summation, where the sum went from Q1 to Q2 of a to the n. You remember? It goes the first term, that would be the whatever a is, in this case, e to the j omega to what? The power, or e to the, j omega minus j omega to the power minus b, right? Well, the minus signs times each other give us a plus. Then it's going to be minus that e to the minus j omega to the power b plus 1, right there, right? Divided by 1 minus e to the minus j omega, correct, class? Now, what do you think I'm going to do with this from this point on? I don't think I did this here. Take a guess. Does that look like a function I can just read through and see what it looks like?
Son.
Yeah, I'm going to turn it into signs. I'm going to use manipulate and turn it into signs. And here's how I'm going to do it. It may not be real obvious to you now. But how about if I factor out an e to the minus j omega here over 2? Watch what happens. If I do that, I get e to the minus j omega over 2. I'm going to factor it out. And then the first term would have to be what? E to the j beta omega, right? Let me do it this way. Omega, and then it would be beta plus 1/2. Now, remember, the j omega 1/2 times e to the minus j omega half goes to 1, right? So I'm back with just e to the j omega beta, right? What am I left with down here? That would become minus e to the minus j omega, and it would be beta plus 1/2. Y'all see that? Because there was a 1 there originally, I'm pulling a minus j omega over 2 out, so there has to be a 1/2 left. Y'all see that, class? Give me a show of hands if you do. I know it's a weird one. Y'all see that? You don't trust me. That's all right. It's still right. It's still right. I'm not trying to sell you insurance. Next, I'm going to do the same thing down here. This one's more apparent. Can I just factor out an e to the minus j omega over 2 on this one? And if I do that, what do I get? E to the minus j omega over 2 there. Now I get e to the plus j omega over 2 here, minus e to the minus j omega over 2 there. Don't I? Class, how many see this? Remember, you add the superscripts here, they give you the value, so it would be e to the 0, which is 1, right? Add these, which would be e to the minus j omega, which is the original thing we had there. Correct, class? How many see this? It is obvious. This one's a little irritating on the top one. Now, y'all agree that this could be turned into 2j times the sine of omega over 2? How many see that? If you don't, I'll put it down here. I'm sympathetic. Sine of what? I'll just put sine of what? Theta is equal to e to the j theta minus e to the minus j theta over 2j, right? So if I have e to the j theta minus e to the minus j theta, I really have 2j times sine theta. Theta in my case is the argument omega over 2. You all see that? Or excuse me, for the lower one's omega over 2. The upper one, it's going to be beta plus 1/2 times omega. So this whole thing comes down to, and by the way, do you all see how these cancel nicely? Thank God. So now, this thing turns into simply the sine of omega times beta plus 1/2 over, got something to say about this, the sine of omega over 2. And that is the actual inverse transform of a pulse function. I can actually call this, I guess, pulse omega would be okay, even though it's not completely right. I got something to show you about this. Do you all see that? Now think about this, and this is the way you should always think about this stuff. When you had Fourier transforms for continuous time, they always are analogous to what we got here. We had a delta function in continuous time, you get a constant frequency, right? Same here. I get a phase shift, right? With a delta function, it just brings out an e to the minus j what? K times small omega there. All these things parallel what goes on in continuous time. This one, not quite. For this one, it would be like exponential decay. And if we have e to the minus at u of t, the Fourier transform of that is what? 1 over a plus j omega, right? Here, we don't have that a plus j omega. Now we really have, you could say 1 minus, 1 over 1 minus this. Well, this is something I'll talk about a little more later, but really the reason we have this and not the 1 over j omega or j capital omega plus a constant is because, remember, our entire frequency domain is condensed down from minus pi to pi. Instead of going from minus infinity to plus infinity like we had in omega, everything's squeezed down. Follow me on this, class? And I'll show you actually how you can draw an exact analogy to get, if you use the Fourier transform to get this, or if you use the DTFT to get the actual Fourier transform of an exponential decay, but that'll be a little later. Trust me on this. This stuff does work. It is analogous. Now, for this function here, this is an important thing to know. Does everybody know that for small arguments of x, x is small, that the sine of x is about equal to x in radians? Y'all know that? When you're talking about radians, if you have the sine of pi over 100, it's about equal to pi over 100, all right, in radians. If you're talking about the sine of pi over 100 radians. About equal to pi over 100. Now, when you look at this right here, there's two things I'm going to say. This right here, for small values of omega, is about equal to omega over 2. Do you follow me on this? For small values. Following? Not large values, don't go there, but for small values. Doesn't this look like a sync waveform? Isn't this starting to look? Yeah, you would have to multiply by beta, right? And you'd have to put a beta up top, but ultimately we can manipulate it to make it look like a sync. This thing, it has a lot of different terms. People call it an async waveform, I think, sometimes. But what it does look like, and this is important, is this. If I take a look at the sine, or I'll just put capital P of omega here. Now, I want you to take a look at this. At 0, you would have to use L'Hopital's rule on this, where omega is 0, correct? Because sine of 0 is 0, isn't it? And we have 0 over 0. You do L'Hopital's rule on this, you're going to see actually what you get is a value of, that the height of this is equal to at 0, if you took just the magnitude of this, would be equal to, I believe, it's equal to 2 beta, or 2 times b, but I'll check on that. And then what it does is this, and I want to make sure you understand this. So this is magnitude. It looks more or less like a sync function. And what happens is the first 0 here, where would the first 0 be if this was capital omega, just so you took a look at this? How would you get the first 0 where this function is 0? Well, remember, this is slowly varying, right? Now, what do you notice? Where does the sine go to 0? At pi would be the first. Remember, at 0, then it goes at pi over 2 to 90, right? I mean to 1, pi over 2. And then at pi, it goes to 0, correct, class? So we'd set that equal to pi. So we'd say omega times beta plus 1/2 equal to pi. Or we can say omega is equal to pi over b or beta plus 1/2. Now if b is large, like 10, 15, right, or the width of that pulse is large, you can see this is starting to look small, right? And the first null would be at pi over, what would it be? If it was 10, it would be, was pi over 10, about 18 degrees, 17 degrees roughly. All right, follow me? But you can then see where the first 0 is, the next 0, and you can see this is asymptotically, the envelope that holds that there is really the 1 over the sine of omega over 2. That's the envelope. Follow me on that? Like before it was the 1 over x, it was a sync function. So it's similar to a sync, but not exactly. That's the thing about this. And that's real important. You'll see that later. I don't want to spend too much time on this until I have something more concrete to work with. All right, now those, there's two other functions I got to give you down here. I'm going to leave that up. Most people, you're not going to really appreciate the DTFT until you see how useful it is in bringing about an understanding of the DFT. That's coming up, and that's a finite series instead of an infinite series. All right, next one. So this one right here is really going to be the sine of b times, b plus 1/2 times omega. This is going to be the sine of b plus 1/2 times omega over the sine of omega over 2. That's the pulse function. I'll probably give you this one right here. All right, the reason I'm saying that is a lot of people mess up that 1/2 business. They just do. But it's straightforward. Now, after that, I'm going to do 1, and 1 simply goes to, well, what was 1 when it was in continuous time? If you had DC, what did it go to in the frequency domain? Think about where all the energy is, first of all. If it's DC, where's all the energy in terms of omega? At omega equals 0, right? And do you remember with duality, we get a 2 pi from it, 2 pi times a delta function. We know this would be 2 pi right here times a delta function normally, right, for continuous time, a delta of omega. Now, because this thing repeats itself and I'll prove this in a second, every 2 pi, what you need to do is put capital, you got to put a delta function in there, and it's omega minus 2 pi times k, and then to make it right, you have to put a summation like this, where k goes from minus infinity to infinity. Because basically you have delta functions up and down the frequency, the omega domain, all at omega equals 0, omega equals 2 pi, 4 pi, and so forth. Got me? The height of those deltas is given as 2 pi. I don't blame you looking at me suspiciously. That's important, and I'll prove that in a second. There's a function called the SGN function, signet function. We do use that. You're going to see later on when you get in your upper level courses, these functions appear all over, especially if you're in doing anything with communication, signal processing, probably like some of the Wi-Fi courses that do a lot of this stuff that Dr. Tugney teaches. We use this also. Don't know that for a fact. But if we have I think in his book he uses SGN. SGN of n is really equal to 1, and that's for n greater than or equal to 0, and it's minus 1 for n less than 0. So it's just either 1, it's minus 1, then it goes to 1 at the transitional point at 0. Follow me? Now that function, up to it here, if I have, I'm not going to do the sum on this one. That one simply goes to, and I'm going to use his method, it's just 2 over 1 minus e to the minus j omega here. And then for u of n, this one will go to, well, I could show you the u of n function, but I want to just mention something. You know, if I put, isn't this like a to the n times u of n, where a would be 1 here? Right? So if you look back here, when I had a to the n, it went to this, right? But if a is approaching 1, we know we're going to have the 1 over 1 minus e to the minus j omega. We know that. But this is the thing. This has values for all n greater than 0 of constants, so we will definitely have energy at DC. I'll prove this one too. I'm going to have to use duality to get it. Do you follow me in this class? And that means you're also going to have the 1 over 1 minus e to the minus j omega, just like that, with a approaching 1. But then you're going to go have this thing plus the summation k equals minus infinity to infinity, and you're going to get the pi. In his book, he's doing it this way, times delta of omega minus 2 pi k. That just puts impulses all up and down the omega domain. Basically, an omega equals 0 where the energy is. And I'll do this with duality. Now I'm going to just mention a few of the properties. Sorry. A few of the properties, and I want to show you a couple things. I got some time too, I'm glad I did. For the properties, you all know linearity. Linearity is a straight shot. If I have x of n goes to x of omega, I'm not going to put this one up. Then I know 5x of n goes to 5x of omega. Got it? And if you have x of n plus y of n, if x of n goes to x of omega, y of n goes to y of omega, and if you add them up, then you get x of omega plus y of omega. X is the transform of x of n plus y of n. I'm not even going to bother with linearity, it's obvious. When I talk about time delay, write this one down if you don't know. This is stuff, these are properties now that we need. When we talk about properties, if I have x of n go to x of omega, that's my assumption. Then I can say, if I have x of n minus constant, call it constant k, that brings out a phase. It's simply e to the minus jk times omega times x of omega. Same as the Fourier transform properties. You're going to see almost all of them are the same. What page are the properties on in your book, by the way, guys?
395.
395? All right, that's a simple one. This one isn't used that much, but x of minus n is going to be x of minus omega. It's the same as with the Fourier transform. X of minus t gives you x of minus omega. Same thing with Fourier. It's used for to get information for negative sums. Though that's true. Now, n times x of n, this one. I want you to think about this for a second. What was t times x of t, Fourier? Guys? d omega of x of omega. Wasn't it, guys?
Yeah.
How many remember that? Even if you don't remember it exactly, you remember hearing it somewhere. Well, this is the same thing. It's going to be j times d omega. You're going to be thankful for this. Of x of omega. That is so nice. It parallels exactly, doesn't it? Then, this one you'll get. I can prove it if you want me to. If I had x of n times e to the j and omega naught. Now, I have a comment about this in a second. Just write this down. This one I want to comment on. Always go back. Think of Fourier properties. If I had x of t times e to the j omega naught t, that e to the j omega naught t really is what? It's like one component of what a sine or a cosine is, right? It's at a constant frequency, correct, class? We almost know what's going to happen in the other domain. A phase, if you get a phase multiplier in one domain, you're going to get a time delay or a delay in the other domain, right? So in the other domain, here's exactly what it's going to get. You're going to get what, guys? X of, now it's capital omega minus omega naught, right? And that's, I hope these properties are shown in your book. Are they in your properties? You got it? The next two follow from that, and they're the biggies in my opinion. All these properties can be used to get almost anything. I'm going to put it right here. And we'll do problems a little more time, a little more time. Now, the next properties is going to be modulation. You know I'm real big on modulation, right? I'm going to do the cosine one first. If I have x of n times cosine of omega naught n, or I ended up with x of n, I hope they have both of these in your book, times sine of omega naught n. We're going to do the properties on these. Now first, when we did it in continuous time, do you remember if it was x of t cosine of omega naught t, over this domain, what happened? It would become 1/2, right? And then I'd take x of omega, assuming I knew it, right? And I'd replace omega by omega plus omega naught. Do y'all remember that? So then this becomes x of omega plus omega naught. What's next? A plus symbol, not a minus. It's cosine, right? It's even. But then it's going to be x of omega minus omega naught, correct? I'm going to remember that. In the continuous time domain, it was small omega, right? But it's the identical transform parity. And it assumes you know the transform of x of omega. X of n goes to x of omega. Got it? Now that's modulation, remember that. What about the sine? There's two differences. What are the differences? J over 2, very good. J over 2 times, this is the same, omega plus omega naught. Keep going. Minus x, very good. Minus omega naught. And those are modulation, and I'm real big on those. So important. Okay, class? What? Oh, I'm just making sure I didn't miss somebody. Now, convolution in time, same thing as before. If you have x of n convolved with h of n, convolution in time or in discrete time is just going to be x of capital omega times h of capital omega. Multiplication of frequency. Got it? Yes. Okay. Everybody? One thing that's going to be a little bit different, and I need a piece of the board to do it. I'm going to do it over here. This is important, so make sure you write this down. This is important. And it does have an analogy, it's got an analogous property in the time domain, but there is, it's a bit obscure. So listen, suppose now I want the transform of a summation, write this down carefully, of x of I, where I goes from 0 to n. So this is like integration, you know, summation of time. The summation discrete time is like integration of continuous time. So now I've got that. Well, I want to find a transform of this. Now it assumes, listen to me now, it assumes you have x of n and you know it goes to x of capital omega. Got it? We know that pair. Now watch the trick on this. We're going to define a new function. We're going to call that v of n. Got me? Work with this. Y'all see that? Next thing we're going to do is this. Now I'm going to say that, well, v of n could actually be expressed as the summation from I goes from 0 to n minus 1, x of I, plus x of n. Please take a look at that. Y'all get it? Y'all agree with that? You're looking real suspicious. I'm not sure what you're up to, but it's not good. Y'all with me on this? I just what? The sum I broke off the top, the last sum part of the sum, and added it out here. Y'all see that? Now, watch. Isn't this really, this is v of n equal to the v of n minus 1 plus x of n, isn't it, guys? Convince yourself of that before I continue. Y'all agree? Other people know it lies. It really is true. I don't believe it. Are you agree with me? All right, now the next thing I'm going to do is take the transform of that. And notice what happens. I can take the transform of this and I'm going to have v of omega, I don't know what it is yet, right, is equal to, well, if I know v of omega, then minus 1, don't I have just e to the minus j omega times v of omega here, plus x of omega. You follow me on that, class? Sneaky, right? What am I going to do now? My goal is to get v of omega. How about take this to the other side, and then I get what? V of omega, and I would have 1 minus e to the minus j omega, right? You all see that? So it would be v omega, and it'd be times 1 minus e to the minus j omega is equal to x of omega, right? And finally, you see that v of omega is equal to, I got something to tell you about this, x of omega over 1 minus e to the minus j omega here, but I have to tell you one thing, I don't have time to prove it, we're already out of time as usual. In there, you're also going to get this. You got to add this to it. And this may be 0, but you're going to have to add a summation here of pi times x, and then it's going to be 2 pi k here, and times delta. Do they have the sum shown in this in your properties, by the way? And this is going to be k goes from minus infinity to infinity, and it's going to be times delta of 2 pi times k. Oh, it's sorry, omega. This is omega minus 2 pi k. Now the reason for that, and I'm just going to tell you, this, I could write it another way. In your book, you see something like this for the summation property in the properties. Take a look in your properties. Do you have them?
For DTFT, right?
Yeah, DTFT properties. See the thing with the sum? For the DFT, I mean for the Z transform, it won't have this. I'll get to this later. This has something. There's a few more things I got to say about this, and I didn't get to duality yet. The next time we will, I'm going to give you some homework on this. And let's see, on Friday for the quiz, what we're going to do is this. We'll do it on basic DTFT problems. Nothing, just basic ones. And I'll give you a set of them. Now, you haven't had any DTFE, you had the filter properties last time. So I'll give you a set, make sure you do them, and I'll give you the answers, okay? All right, now, I need to see you, and where's the other guy that's gonna take the mic?